It is an immense pleasure for me to welcome you to this special colloquium inserted in the webinar series of the graduate program in physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave the microphone and camera turned off, except for the moment you're going to speak. Questions will be allowed in the end, unless otherwise requested by the speaker. The questions can be asked using the chat, both in this virtual room and in the YouTube transmission. Today, we have the great honor to listen to Professor Michael Stanley Whittingham, who was awarded with the 2019 Nobel Prize in Chemistry, together with John Goodenough and Akira Yoshino, for the development of lithium-ion batteries. Professor Stanley Whittingham was born in Nottingham in the United Kingdom. He completed his bachelor, master, and PhD at Oxford University. After a postdoctoral fellowship at Stanford University in the United States, he worked for the Exxon and Schlumberger oil companies before becoming a professor at the State University of New York at Binghamton in 1988. Professor Whittingham is a member of the National Academy of Engineering of the USA. Presently, our special guest is Distinguished Professor of Chemistry and Director of both the Institute for Materials Research and the Materials Science and Engineering Program at Binghamton University, State University of New York in the United States. He also serves as Director of the Northeastern Center for Chemical Energy Storage in the U.S. Department of Energy at Binghamton. Apart from the Nobel Prize in Chemistry, Professor Whittingham's research has been honored with various recognitions, including Chancellor's Award for Excellence in Scholarship and Creative Activities and Outstanding Research Award from the State University of New York in 2007, Award for Lifetime Contributions from the American Chemical Society in 2010, Thomson Reuters Citation Laureate in 2015, International Society for Solid-State Ionics Senior Scientist Award in 2017, and Turnbull Award, Materials Research Society in 2018. The lithium battery, from a dream to domination of energy storage, is what Professor Whittingham will tell us about today, and I should not make you wait longer to listen to him. Professor Stanley Whittingham, thank you very much once again for having accepted our invitation, and from this moment on, the audience is all yours.
Thank you. Thank you very much for that kind invitation. Obviously, I would like to have been in Brazil in person. I have visited Rio twice in the last 10 years, and my wife spent many years of her childhood growing up in Rio, so she knows that area very well. What I'd like to do now is really discuss the beginnings of the lithium-ion battery, and particularly how we can use the lithium-ion battery to help mankind. So let me thank first the United States Department of Energy, who supported much of my work for the last 30 years and still supporting it today. At the bottom of this slide, I show you three fairly modern applications of lithium-ion batteries. A Tesla car, one of the original ones here, is the lithium-ion, and all your devices, whether they're phones, laptops, watches, all are dependent on lithium-ion batteries. Then the other two pictures show you the sun and the wind farm, both of which are very dependent on storage. And you can see on this wind farm on the right here, a 32 megawatt hour storage facility down here, which shifts the electricity and smooths it. Let me just show you what I plan to talk about today. I'll talk about the beginnings of the lithium-ion batteries in about 1972, how we developed it, and then show you some examples of where it's being used today and how it's dominating. I'll show you why we need batteries for a cleaner environment. I'll discuss what they are, what their limitations are, and really then some policy, or if you like, political comments about how we need to do science in the future. So let me first thank Exxon. It was then Esso, and nowadays is known as ExxonMobil, who had the foresight to invest in energy storage as well as fuel cells and solar cells. So in 1972, we started work on lithium-ion batteries, and there was no such thing existing at that point. So we wanted to store energy for electric vehicles, and Exxon wanted to build electric vehicles. And we used these large single crystals of titanium disulfide. And we made, I'm showing you two devices that we made at that time. One is this paperweight, which has a battery in it, a watch, and a little solar cell. This particular one is on my desk right now and is still working, and it's about 45 years old. So you can see a well-made lithium-ion battery lasts almost forever. Beneath that is a much larger battery. This one's about 6 inches by 4 inches by an inch thick. And this was used at the electric vehicle show in Chicago in 1977. And it turned on and off a motorcycle headlamp for the whole week, again showing how resilient it was. Let me just point out again this cell here. If you want to see these now, they're on display in Stockholm at the Nobel Museum. Here's this coin cell and this little button cell next to it, and then the product brochure for the batteries we made in those days. And they were made by a subsidiary called Exxon Enterprises. Okay, so these are in the museum. It took us a while to hunting in basements to find some of these old cells, but they did exist. And my colleagues at Rutgers University tested these old cells, and they still had 70% of their capacity remaining after more than 40 years. Let's look at where they are now, how far they move from these little cells. And I'll show you several examples, and let me start from this little car here, which is a 2-seater that my wife and I drove in Bermuda. The island of Bermuda does not allow tourists to drive cars, but they passed a law allowing tourists to drive small electric vehicles in 2019. And this particular vehicle, I think, was about 2 weeks old when we drove it. And you can see we're charging it there. So that's one extreme of electric vehicles. To the right are 2 other electric vehicles, what we call a 16-wheeler, a large truck, and next to that, a garbage truck. Garbage truck, that's ideal for electric vehicle. It stop, start, raise, lower all day long. And I had the opportunity of driving both these at the Packard Peterbilt test track north of Seattle, Washington, 2019. Beneath that are 2 more electric vehicles. This is a Jaguar, and to the right of it is a London taxi, totally electric. And the British ambassador took these to Stockholm for the Nobel ceremony and drove to and from the palace for various events in the taxi. So electric vehicles are becoming dominant, and I think Britain was the first country that has announced banning of sale of internal combustion engine cars after 2030. I've already shown you these pictures of renewable energy and the importance of batteries there, and we'll go into that a little bit later. Let me show you another application of lithium-ion batteries that we met whilst in Stockholm. These are 2 astronauts on the International Space Station. The lady is an American whose mother was Swedish, and the gentleman is from Italy, and they had just completed installing lithium-ion batteries to store the energy from the solar cells on the outside of the International Space Station. had replaced the old nickel metal hydride batteries, and the lithium batteries are very pleased with. They weighed half the amount, had half the size, and would last twice as long. So lithium-ion batteries are going basically, I would say, all around the world. Any energy storage application you can think of, they're in now. If you buy a electric razor or any garden tools, are invariably all lithium-ion today. So let me just make a slight comment about the virus. And as we go back to normality, we should not go back to the old normal. As we invest in the future, we should invest in cleaner energy and not build more coal power plants, not build more oil refineries, but build more renewable energy. So this was a editorial that 200 of us artists and Nobel laureates published in the French newspaper Le Monde about a year ago. So let me show you now why renewable energy is beginning to dominate. One does not need subsidies to make renewable energy effective. And I show you two examples here. One in Texas, which is a bit awkward considering the issues they had the last 2 weeks with their storms. In Texas, as of last August, over 94% of all the planned new energy capacity was renewable. And you can see from the plot on the right, this is solar, wind, and storage. The remaining 6% is mostly gas, with a little bit of coal and essentially no nuclear. The big advantage of renewable, it needs minimal staff to operate. There's no fuel cost during operation. You don't have to ship oil, gas, or coal in. It comes from the sky, as it were. So once you've built the facility, it's much lower cost to operate. But they're all intermittent. So we've got to have storage. And I show you on the right a new storage facility. This is 1.2 gigawatt hours. I think it's 4 times the previous largest storage facility, one of which was in San Diego, California, and the other one was in South Australia. So this is, I'd say, by far the largest in the world. And it started up last December. The building there is an old gas-fired power station. They decommissioned that, and the building is now full of lithium-ion batteries as well as the ones on the outside. This is planned to increase to 1.6 gigawatt hours this year, and it's been approved to go to 6 gigawatt hours. So this is far larger than anybody could have imagined even 12 months ago. So lithium-ion batteries are viable, they're cost-effective for these sort of applications. Let me step back for a moment and just discuss energy in general, really the life cycle of energy. We produce energy, and most of it is one-time use. That comes from oil, gas, or coal. There's also renewable. Includes solar, wind, and hydro. One of the issues with energy is we make it in one place and we use it in a different place. So how do we transport it and how do we store it? Because different times of the year we use vastly different amounts of energy. So in the United States, we use much less energy in the spring and the autumn than we use in winter and summer. So you have to be able to store the energy for those times. And the other one is you as a customer demand instant gratification. When you turn the switch, you want the electricity to flow instantly. One way to help manage energy use is to increase energy efficiency. And we've seen this where the incandescent light bulb, which is only 10% efficient, is being phased out very fast. But at the same time, utilities have to make money. And so you have to have political decisions as to how they can make money if they actually cut back on the amount of energy they sell. And certainly in New York State, they make money on the capital equipment they invest in, not on how much energy they actually make. So let's look at how we can store energy and why we need to store it. This is a typical usage curve. As you can see, the usage, this is 24-hour period. At nighttime, we use very little energy. This is this dashed line. As we wake up in the morning, we use more energy. And late afternoon, when folks go home, there's a peak of energy production, and then it decays again in the evening. So a utility has to have power plants in place to address this peak, which means they're very wasteful. In some cases, they may be only used 5 or 10% of the time. So the ideal would be if we could have a larger power plants. We store energy at nighttime. So we fill in this, if you like, this valley at nighttime. We then use the energy stored at nighttime to fulfill the needs at the peak here. So we try to flatten out this whole system. So we then can use more what we call baseline power plants that operate all the time at maximum efficiency. And this includes power plants like nuclear, which operate best if they're not turned on and off. The challenge now with renewable energy is they don't occur at the right time of day. So in the US, particularly in Texas, which is the largest producer of wind energy, the wind blows hardest at nighttime when we don't really need it. And for solar energy, the maximum is in the middle of the day, where again, we don't really need it, we need it later. So we need to shift both of these, the wind over to the morning and the solar to more the evening. There are several ways of storing energy, and by far the largest means is pumped hydro. A number of countries, I think Brazil has hydro stations themselves, but in the US, we have several states that have large pumped hydro systems. This is where you pump the water to the top of a hill, and then when you need the power, you let it flow down through turbines and generate the electricity. I show you a picture of such a system. It's about 100 miles from where I am. It can generate 1 gigawatt hour of power. And challenge here is the startup time is about 2 minutes. So you need a short-term system as well to fill in that gap. The big issue with pumped hydro, there's very limited new sites. It's very difficult to get permission to build new ones. What they are doing now is upgrading all the old ones, putting new turbine pumps in. So they're now over 73% efficient, which is much higher than they used to be. Batteries that convert chemical to electrical energy are by far the most flexible and the most common. They can be portable, they can be stationary, they can go from milliwatts to now we've seen to gigawatts, and you can turn them on and off in a matter of seconds. So you can use a battery system combined with a pumped hydro to smooth the grid. A third system is flywheels, which is kinetic to electrical energy. There's very few of these. There's one near the state capital in Albany, which is used for power smoothing. The challenge here, the very high speed they run at, they're hazardous, and so they're not likely to be used for mobile applications. So let me just talk a little bit about batteries. All batteries are based on what we call intercalation chemistry. So let me first define what intercalation is. Every fourth year, the leap year, we intercalate February 29th into the calendar. Then the next year we take it back out. So it's what we call a totally reversible process. We can put it in, we can take it out. If you look at an old dictionary, that's what the definition will be. In science, we use it in exactly the same way as the reversible insertion of some guest species into a host lattice. The guests can be ions, they can be molecules. The host can be inorganics, they can be biomaterials such as DNA, a whole host of things. And I show you an example here of titanium disulfide, and I'll show you a model a little later on. So we have what we call blocks here, sulfur, titanium, sulfur. Then we have a van der Waals gap here, so very, very weak bonding. So this will interact with things like lithium, and lithium will insert in here, and it expands this lattice by about 10%, but does not change the lattice in any other way. So we break no real bonds, so we can take them in and take them out very easily. So let me now move on and show how this works in a battery. So all lithium batteries, lithium-ion batteries, are based on intercalation reactions. So this is a battery. Every battery has an anode, it has a cathode, and in between it has an electrolyte. And the electrolyte in this case allows the transport of lithium ions from the anode over to the cathode. At the same time, the electrons go through the external circuit doing the work you want it to do. So this electrolyte has to be stable, only transport the lithium ions, and that fully charged, all the lithium ions are in the anode. These are little green ions here. In this particular case, I'm showing you graphite. And on the other side, at fully charged, there'll be no lithium ions over here. So this is, again, a layered structure. Both these are layered structure. And the voltage we get in this cell is just a difference in free energy of formation of this compound, the anode compound, versus the cathode compound. Obviously, we've got to get electrons in and out. So both these materials have to be electron conductors, as well as allowing ions to move. And we have current collectors, which collect the electrons and shift them. So we have these on both sides. So let's briefly look at lithium titanium disulfide. Why was it special? It is essentially, for all practical purposes, a metallic conductor. So electrons can move in and out very fast. This means when the lithium ions move, they're shielded from the electrostatic interactions with the host lattice, so they can move very fast. The other advantage of this particular compound, it is what we call a solid solution. So the structure doesn't change at all from 0 lithium to 1 lithium. And you can see this in this voltage plot. This is the cell voltage. You could put free energy here. It's the same thing. You see the voltage slowly decays in a continuous manner, so showing this is single phase. Then when we reverse the current, we recharge it, it follows exactly the same curve. This curve drops because as we put the electrons into this titanium disulfide, we're filling up the conduction band, so we get less and less energy as we put more and more electrons in. I should point out this was run at 10 milliamps a square centimeter, probably higher than any lithium battery today. And we did not have to use any conductor added to the material, so there's no carbon black in here. And I'd like to thank my team, I put at the bottom here, who did a lot of the work, and leadership from people like Al Shrisheim. So this is the structure of TiS2. These are TiS6 octahedra. In between them are our lithium ions, which we can take in and out. So TiS2, in the end, is not unfeasible for batteries because it was in the end found to be too low a voltage, and I'll show you the changes that occurred in time. But it's still studied today. It is still a model compound because of its what we call soft conducting lattice. So we can get sodium ions in there. The structure is much more complex with sodium because it's a bigger ion. So it actually has to separate the layers to get in there. So we get these different phases. And doubly charged ions like magnesium can also go into the lattice. And this is work of Linda Nazar at Waterloo University. And this is the best data that has been obtained to date on magnesium. You can see a smooth curve, just like the lithium one. The red line shows the capacity with time, again, very good. But to get this to work, she has to go to 60 degrees centigrade and use a much lower current density. So a doubly charged ion has more electrostatic repulsion as it jumps through the lattice, so moves much slower. So you can see the voltage here also for magnesium is almost a volt less than for lithium. So in the end, a magnesium battery has only about half the energy density of a lithium battery. So magnesium batteries are not really viable, even though there've been lots of talk about them. It might be more interesting calcium, if we can get calcium to work, because the calcium voltage will be closer to that of lithium. Let me show you why we only have lithium-ion batteries today. This is a typical lithium battery. This is showing lithium metal itself, and this is work of a colleague of mine, Russ Chianelli, again back from the 70s. When you plate any metal out, you tend to get dendrites formed, and this is what a dendrite is. And the reason for that is as soon as you get a little protuberance, like we show here, then the voltage drop from this point, or the field, to the other electrode over here is higher. So once this starts, it keeps on going. And you get the formation of these dendrites that then puncture through what would normally be a separator separating the two electrodes. If that happens, you get a battery short, and you can see you burn out the battery. And these were, in fact, solid-state batteries using polyethylene oxide separator, built by Aristor in Canada and deployed by AT&T, and these, I think, were in Texas. And they had about 4 or 5 of these burn up within the first month. So there are essentially no lithium metal batteries on the market, with one exception today, and I'll get into that a little later. So that's why we always store the lithium in another material, in graphite and aluminum or something else. So let me go back to this battery plot and show you a little bit of the history now. So in 1972, we at Exxon used lithium metal. We learned that we form these dendrites. So we switched to using aluminum, and lithium reacts with aluminum at room temperature to form this one-to-one alloy. And this works well for maybe 100 cycles, but it's not very long-lived. It was Akira Yoshino in Japan, who was working in carbon materials for batteries, who found out that graphitic carbon, as shown here, intercalates lithium very easily if you have the right electrolyte. So a challenge with carbon is if you have the wrong electrolyte, then the solvent will solvate the lithium, and the solvent will go into the structure as well, eventually destroying it. So this graphitic carbon is still used today. It came on the market around 1990, still used today. But it takes up half the volume of the cell and a substantial weight, so it has to go eventually. So we're looking, and others looking at replacing it with tin or silicon. Both these react with 4 lithium ions, but there are issues here, so we'd like really to go back full circle and work on lithium metal again. On the cathode side, I mentioned we started out with lithium titanium disulfide. John Goodenough, who was at Oxford at the time, studying the magnetic behavior of lithium cobalt oxide, recognized it had the same structure as lithium titanium disulfide. He tried it in the battery, and you know all the history since then. It dominates, and if you've got a cell phone, you've still got lithium cobalt oxide inside it. But cobalt is very expensive. It's also has child labor issues in the Congo. So much of the cobalt has now been replaced by nickel and manganese, or in the case of people like Tesla, by nickel, cobalt, and a little bit of aluminum. And I'll discuss these in the next few slides. John also came up a few years later with these phosphate materials. These are more stable, and it turns out the iron phosphate is a naturally occurring mineral. But the challenge here is this has much lower energy density because you're now carrying a heavy phosphate group with you. My colleagues are working on the manganese analog. This has a higher voltage and so may be advantageous. We are working on putting 2 lithium ions into phosphate structures in order to get the energy density back up to that of the layered oxides. So let's look at just what the energy densities of these cells is, and therefore why we need still to do more research. Don't worry about all the numbers on here. Just look at the numbers within this red circle. This gives you the percentage of the theoretical capacity that we actually have in today's batteries. So it varies from 11%, the maximum is 25%. This is on the volumetric basis. If you look at the weight basis, it's 25%. So it's a huge opportunity of improving this. And I'm part of a Battery 500 consortium whose goal is to get this number up to 500 watt-hours per kilogram. In other words, get our efficiency up to 50%. To do that, we've got to get rid of most of the carbon. As I said, it takes up half the volume. We need 72 grams of carbon to store 7 grams of lithium, so not very efficient. We need to use higher lithium content cathode materials. So the layered oxides, we only use about 60% of the lithium today. We need to get that up, and we need to use more than 1 lithium. The other thing is we need fundamental research to improve the physical properties of these materials. We have to make them better ionic and better electronic conductors. We could then use thicker electrodes and therefore reduce the amount of dead weight to things like current collectors and separators. Let me show you what some of the challenges are working with these layered oxides. This is a typical formula of a layered oxide: nickel, manganese, cobalt, and aluminum. So we call them NMCAs. As I mentioned, cobalt dominates electronics today. For most other applications, it's the mixed metal ones. There's a huge effort ongoing now to reduce or try to eliminate all the cobalt. This would cut the cost significantly. And for that reason, in electric vehicles, we've gone from 33% nickel, and I should say the formula we use here is shown at the bottom. So if you've got 622, it means 60% nickel, 20% manganese, 20% cobalt, gone from 30% to 60%, and now some vehicles are all the way to 80%. The challenge here is we put more nickel in, these materials become less stable. So if you look at this formula, if you take the lithium out, you then got 4 plus cobalt, 4 plus lithium, and this is thermodynamically unstable. They will want to release oxygen, and given the right conditions, they will do. So let's just look at the thermal stability. So if we get these materials, the most thermally stable one only has 1/3 lithium in it. It has the lowest capacity, 160 milliamp hours per gram. If we want to get up above 200, then we have to go to higher nickel. This one is 85%. And you can see its thermal stability is 100 degrees lower. Though we hope the lithium batteries never get to this temperature, the thermal stability is a measure of how reactive these materials are with the organic electrolyte. So if they react, we lose capacity. So this directly relates to this capacity retention on the right-hand side. And our goal is to get into this blue box: high thermal stability, high capacity, and high capacity retention. So one of the ways of helping a little bit here is put some aluminum in, but that's going to reduce the capacity. And ideally, we'd go to more manganese because this is by far the lowest cost material. So where do we stand on these materials today? This is our Battery 500 consortium. This is out of Pacific Northwest National Lab. So Jay Xiao leads this effort. She's an ex-PhD student of mine. So she makes batteries of this type. We call these pouch cells. And then these are tested at Idaho National Lab. So we make them in one place, test them in another place, so it's totally independent. The material we use for these tests is 60% nickel, and it's formed in these what we call meatball morphologies. So you can see the primary particles here are maybe 200 to 300 nanometers. They're then formed into these secondary particles of about 5 to 10 microns. We need these large secondary particles so it packs better and gives us a higher density. So here's the data we've got so far. So the project started late 2016. So by 2017, we'd got about 40 cycles at 300 watt hours per kilogram. 2018, we'd got up to over 200 cycles, also at 300. By 2019, we're now up to 250 cycles, but now at 350 watt hours per kilogram. And today we're over 400 cycles at 350 watt hours per kilogram. So it's continuously improving. What we did to do this, we had to change the electrolyte from the standard ones, and we're now achieving 400 watt hours per kilogram for a few cycles. So we're meeting the goals, getting closer and closer to 500. We're using pure lithium metal in here, so this may cause some safety issues, but we're handling that. But one of the things we have to do is use all the lithium metal. So a challenge on this material is when we charge it up, and now we're working on the 80% material. When we charge it up, here's the charging curve. You can see we're getting to about 230 milliamp hours per gram. We discharge it down here. We then, you notice we lose about 30 milliamp hours per gram on the very first charging cycle. This is between 10 and 20% of the capacity. We have to recover that. So we've been looking at why this occurs. So we've been looking at what are the causes of it. And we've concluded that the main cause is low lithium diffusion at high lithium contents. So this is the diffusion coefficient. This is the amount of lithium. And the solid circles is the diffusion coefficient as we put lithium in. So you can see this is pretty constant till we get close to 75% lithium, and then it falls off a cliff. So this diffusion coefficient is dropping by roughly 3 orders of magnitude. So we're having very great difficulty in getting the last 20% of the lithium into the structure. And you can think of this just as if you're in class in person right now. You're in a large lecture hall, and 75% of the seats in that lecture hall are filled in a random manner. To fill in the rest of the seats, which invariably are in the middle, everybody has to move. So this is the same in this lithiation. For these last lithium ions to move in, all the lithium ions in the structure have to go in a more of a close pack configuration. And this is what's causing the issue here. And the actual mechanism is here is a die-vacancy mechanism. So we need 2 vacancies in order for the lithium ion to jump. This is not an issue in taking the lithium ions out. So here's the open circles are the diffusion for the lithium ions coming out until we get to the very last 5 or 10%. So this is very similar to a lecture hall. At the end of the class, you all leave without any problems. So let's look at how we also tested that this was really a function of the diffusion coefficient. I show you here 4 plots to different charging voltages, 4.2, 4.4, 4.6, 4.8. As expected, we get more capacity the higher charging we go to. But you can also see by the time we got to 4.8, the charging and discharging curves are separated, which means we're getting some polarization, and this is due to decomposition of the electrolyte. What I want to show you here is if we discharge at 2.8 volts, then hold at 2.8 volts, we can get more of the lithium in. This is this one, same here, same on the green one. And the same on the blue one. The blue one is not quite as good because you've got these decomposition products there. But if we wait, we can get the lithium back in. So what we decided to do is the same experiment at an elevated temperature. So we raise the temperature to 45 degrees centigrade. And I just show you the three here because the black one is too low a capacity to be of interest. You can now see that we've recovered much more of the lithium at 45 degrees, and holding at 2.8 volts gets us a bit more back, but not that much more. The green one is similar, and the blue one is again similar, but you see now this gap here is increasing because we've got these damaging side reactions. So we now know our electrolyte is really only stable up to about 4.4 volts, but if we're patient, we can get the lithium back in. But we have some clues that we should be able to get it all back in just by looking at cobalt oxide, essentially the same structure. And cobalt oxide does not show this first cycle loss. So let's look at this black curve here, which is 80%. Black is room temperature. If we now hold this for 100 hours at 2.8 volts, we get all the lithium back in. The red is the 45s, so just as before, we don't have to hold it so long. And on the cobalt oxide, it's basically the same at 45 and room temperature. So we feel that if we can modify the behavior of this 80% nickel to behave more like lithium cobalt oxide, we should be able to do this by substitution or coatings. We should be able to reduce this first cycle loss. And this is what we've been doing using a little bit of niobium. So we put 1%, 2% of a niobium solution on our meatballs, heated these up, and then we coat the surface with a lithium niobium oxide film, and it diffuses a few nanometers into the material. And you can see doing this, we've now reduced our first cycle loss by about 40%. So we feel by doing this with better materials, we can eliminate the first cycle loss altogether. And you can see this doesn't matter whether it's 1%, 2%, or 3%. It has the same effect. So a very small amount of substitution will modify it. Let me go back now to look at the history a little bit again. I started out with titanium disulfide. Moly sulfide was the next material looked at by Moly Energy in Canada. It went commercial for a few years, but had lithium problems. I've discussed lithium cobalt oxide. Lithium iron phosphate is the phosphate that John Goodenough looked at. It's a tunnel structure. There's no lithium loss, no first cycle lithium loss in this material, so we know it's possible even in a one-dimensional tunnel structure. Our interest, as I mentioned earlier, is can we put 2 lithium ions into this material? And we chose vanadium as a compound to do it with, because obviously you can put 2 lithium ions in. You need 3 oxidation states, then we can go from vanadium 5 to vanadium 4, then vanadium 3. And clearly this was successful, or I wouldn't be talking about it. And this was one of the 2 items that the US government highlighted in the 2018 federal report that came out in February of 2019. And this was part of our Energy Frontier Research Center. And I want to point out in these research centers, it's a collaboration between 10 different campuses, national labs, and universities in the US, and in this case, Britain. This is one of Claire Gray's students, and this is one of my students receiving this award from the Undersecretary of Energy. So this was a successful exercise. It's not finished yet, but let me just briefly show you a little bit of chemistry as to what we did. This is the structure, has phosphate tetrahedra, vanadyl highly distorted octahedra, called it better described as 5-coordinate. And we made this by a solvothermal approach, mixing a vanadium compound and a phosphorus compound in 95% ethanol. We have to have 5% water in there or it over-reduces the vanadium. And in this case, we've got 2 hydrogen atoms into the structure in place of the 2 lithiums we want. If we heat treat this, we can get those protons out and make a pure phase vanadyl phosphate. So this is what these crystallites look like, little cuboids. They're about 100 to 200 nanometers on an edge. Extremely uniform. You'll see this is the advantage of these solvothermal, hydrothermal techniques. And the electric chemistry of this worked very well. Here is the redox coupled vanadium 5 to vanadium 4 at about 4 volts. And here's vanadium 4 to vanadium 3 at about just over between 2 and 2.5 volts. And you can see there's a number of bumps in here. This is where the lithium ions are ordering. And you can, in fact, you get at room temperature, if you let it stay, you'll get different crystal structures in here. But when you're moving lithium ions in and out, it behaves as a single phase material. Look at very closely, you can see the black curves in here. This is the first cycle. The purple ones are the 50th cycle. And you see, if anything, the 50th cycle is better than the first cycle. So we've got proof of concept that we can, in fact, pump 2 lithium ions into a crystal structure without damaging that crystal structure multiple times. And we're now pursuing this cathode material for uses. It still has some challenges. These vanadyl phosphates are oxidation catalysts, so they tend to react with our electrolytes, so we're looking for better electrolytes. Let me put a few concluding remarks up here. What the present status in the field is that these NMCA cathodes are likely to be dominant, and lithium intercalation systems will dominate, I think, for the next 5 to 10 years. The phosphates will have some key markets, and I expect the markets will grow because they should be lower cost and are more stable. A challenge we have is that we need safer and more stable electrolytes. And ideally, we'd like these to be solids, but we're not sure we can get the right power density out of these. We need new manufacturing technologies. Today, to make a 1 kilowatt hour lithium-ion battery takes between 60 and 80 kilowatt hours of energy. A lot of that is in the mining. And I think a fair amount of the nickel used in these cells comes from Brazil. So we have to look at new mining technology as well as new manufacturing of the batteries themselves. We've got to have clean recycling technologies to make it sustainable. And I expect we're going to see in major city centers like San Francisco, Paris, Tokyo, only all-electric vehicles being allowed. So they'll be cleaner. It's likely they'll also be shareable. So if you look 10 years out, there's a good chance if you're in Rio or another large city, you will get your smartphone out, hit a button, and an electric vehicle will come to your door. You'll get in, it will drive you to your end station. You'll get out, and then it will drive off and pick up the next passenger. So you will not have to worry about charging the batteries. You will not have to worry about parking the vehicle. It'll be somebody else's problem. And I show you on the right-hand side, this is a all-electric Mercedes bus using a solid-state battery. So solid-state batteries are viable. This is using a polymeric battery made in France. It operates, though, at 70 degrees centigrade, so it's not viable for our personal cars. But it just shows you that the solid-state battery can work. Let me just follow up with 3 messages. and leave with you all that science is interdisciplinary. It really knows no boundaries. If you look at the fields of science today, the exciting areas are at the boundaries of the traditional disciplines. So if you look at chemistry, the most interesting chemistry is at boundary between chemistry, biology, and medicine, or between chemistry and materials. And I put these examples here because I'm a physicist, John Goodenough, so I am a chemist, John Goodenough is a physicist, and Akira Yoshino is an engineer. Science is also international. Again, there are no boundaries, and it wasn't for the virus, I might be in Brazil right now and certainly traveling around the world. We publish everywhere, we work across these boundaries, and I'm British, but I made my inventions in the United States. John Goodenough was born in Germany, but is an American who made his inventions in Britain. And Akira Yoshino is Japanese and made his inventions in a Japanese company. I've already mentioned if it wasn't for the lithium battery, you would not have the electronics revolution you have today. Energy storage is enabling renewable energy. It's making everything cleaner. It should assist in mitigating global warming. And I prefer to call this global messing up because, as we all see, we're getting extremes on both the cold and the hot end, even though there's a tendency for the planet to get warmer all the time. And we have a more efficient grid by using storage. Two other points I want to make is that understanding different cultures matter. If we work across the globe, Americans don't think the same way as Europeans, and certainly not the same way as Asians. And I think we have some differences between Brazil and the United States as to how we carry out our lives. So we have to understand each other, and I believe now it helps if we understand the languages, but I don't know if that's all that essential. I know my wife would disagree. She teaches languages, she teaches Spanish, and is a native speaker of both Spanish and Portuguese. And the other point I want to make is that facts do matter, science does matter. And I know the last few years, both in the United States and Brazil, it appears that facts are not important, but fortunately, the United States has made a turn, and I think our present administration is now listening to the scientists. For those of you who would like to read a bit more, these are two, I would say one book and one publication. This one on the right is in the IEEE proceedings. This is their centennial issue from 9 years ago. If there's anything you want to know about electronics, solar, or anything else, there's an article in there discussing the last 50 years and extrapolating into the future. It's totally free. You can download any article from the web. You'll see how fast things change. Some of my predictions are already wrong and gone, but for the most part, they're right. An easy book to read is this book called Bottle Lightning by Seth Fletcher. It gives the history of the lithium battery and goes into some detail about how the batteries were started out, about the lithium in South America and where it's going in the future. And it costs, I think, about $8 on Amazon, and I suspect it's not too much more expensive for you. And I will stop there. Thank you very much, and take any questions you might have.
So thank you very much, Professor Whittingham, for this wonderful webinar. And before we proceed, I would like to ask everybody to turn on their microphones for a huge round of applause in retribution for this wonderful talk. Okay.
Thank you.
So we already have some questions, but before that, while people are stimulated to write more questions, let me give you a panorama of the audience that you had during your talk. So we have about 100 people in this virtual room. If we consider the YouTube, then we have 150. So we have participants from all around Brazil, from north to south, from west to east. So to mention some of the states, we have from in the north region, we have the states of Amazonas, Pará, obviously, where I am speaking from now. From the northeast, we have Bahia, Ceará, Maranhão, Paraíba, Sergipe. From southeast, we have Minas Gerais, Rio de Janeiro, São Paulo. And from the deep south Brazilian states, we have Paraná and Rio Grande do Sul. Obviously, we are organizing this webinar from the graduate program of Pará University, where we have our graduate students, postdocs, teachers, and professors. I should mention Sam, Angela Clautal, Danilo Alves, Newton Barbosa, Jorge Cassimeiras, Valdeci, Valdomiro. Not only from the city of Belém, but also from around. Pará is a huge state, as you may know. So we have the cities of Abaetetuba, Ananindeua, Castanhal, Capitão Poço. We have participants not only, obviously, from the physics program, but also from, for instance, chemistry, like Ana Lima, Eronides Filho, Rodrigo Delanotte, people from geophysics, like Cícero Regis. We have undergraduate students and graduate students, postdoc teachers, and professors from many universities, institutes, and research centers all around Brazil, like, for instance, Alexandre Engler, Eliana Mucilo, Gustavo Dubeck, José de Aquino, José Guerra, Luiz São Paulo, Satis Kuma Viete, and Wendel Alves. And I would like to mention especially Professor Romeu Rocha Filho, who is the president of the Brazilian Chemistry Society, is also here with us today. And we also have participants from abroad, from the United States, apart from you, obviously, which are, for instance, Anderson Janotti and Igor Evangelista from Delaware in the United States. So let me start then with the questions. So I'll start with one that came from the YouTube. It comes from Giovanni Danieli. He is an undergrad student of chemistry. So he's doing scientific initiation in chemistry. So he says he's honored to participate and listen to you, and he would like to understand why, by raising the temperature, you lose the capacity.
Because a battery is really a metastable system. So it only works because we've got films formed on the lithium anode from the organic solvent. And so if you raise the temperature, then both the cathode and the anode react with the organic solvent, and they form resistive films, typically lithium fluoride, on the surface. So basically, a lithium-ion battery is very much like you and I. It prefers room temperature, maybe 10 degrees above, 10 degrees below, and not much different than that. So if we can get a solid state electrolyte to work, then that will remove this temperature issue. So we won't have to control the temperature. So if you get an electric vehicle that has an immense amount of thermal management to keep the temperature under control, and the better ones use liquid cooling or liquid heating if it gets very cold. So it's all related to the reactions or side reactions that occur. So we have to keep the temperature under control. And even these huge grid storage facilities, they're kept at about 21 degrees centigrade by air conditioning within the units.
Okay, thank you very much, Giovanni, for your question, and Professor Whitman from your answer. So the next question comes from Anderson Janotti, that's speaking from Delaware in the United States. So Anderson, would you like to make the question yourself?
Okay, thank you very much for
10:01 a.m.
very nice presentation. I like it very much. My question is, are there any attempts to use hydrogen as the conducting ion instead of lithium? and what are the limitations? And what is so special about lithium, about the lithium ion?
If we use hydrogen, then we're really talking about a fuel cell. And there's quite a lot of work on fuel cells. They've been going on for, what, 2 centuries, I think. The challenge with fuel cells, we have to use noble metal catalysts on the oxygen side. So we use hydrogen as the anode, oxygen as the cathode, and Toyota and others have built cars. They're just much too expensive right now. But again, there's lots of talk about using hydrogen as a storage medium, and in particular, using hydrogen and fuel cells for large trucks. And you can make hydrogen and recharge a hydrogen tank in a minute or two. So if you're going to have a truck, say, going across the United States or across Brazil, you need to recharge it every 200 miles. And you could do that with your hydrogen fueling station and use a large battery for acceleration and braking and so on. So hydrogen is not a battery, really what we call a battery, it's a specialized one. You'd use it in a fuel cell configuration. But hydrogen is very expensive today, so it's not practical, but there's lots of research going on.
Okay, thank you, Anderson, for your question. Professor Whittingham for your answer. So the next question comes from José de Aquino, speaking from São Carlos, São Paulo. Professor José de Aquino, would you like to make the question yourself, or do you want me to read it for you?
Yes, I can say the question, no problem. Okay, thank you very much, Professor Whittingham, for your presentation. So it was really nice to hear to you. Well, I have 2 questions, and more than 2, of course. We know the impact of lithium-ion battery, and however, we must not forget that a significant amount of energy is required to prepare this device, as you mentioned in your presentation. And how we deal with this issue? For example, you mentioned it's required about 300 kilowatt per hour to store 1 kilowatt per hour of energy. So how can we deal with this problem? And how about the global demand for lithium-ion battery? We will be able to supply all the demand? Maybe recycling is an option, and I'd like to hear your opinion about this.
So I think what we need to do is look at what Europe is doing. Europe is spending several billion euros building basically an efficient supply chain from the mine to the finished product. So they're going to do the mining and make some of the most energy intensive battery materials in Scandinavia using hydropower. They're going to be looking at different mining techniques to reduce the amount of energy used, and then just ship the cathode material to Germany, which is not very far. Similarly with the anode material. So we eliminate most of the shipping. One has to understand today, I think, a lot of lithium, maybe half of it comes from South America. It's shipped to China. The graphite comes from somewhere else. It's all shipped to China and cleaned in China, then shipped off to battery manufacturers in the rest of the world. So the materials are, in their lifetimes, probably shipped around the world once or twice before the battery actually gets sold. So we need a supply chain really on each continent. And so a lot of us are pushing that North America needs to do the same thing. We need a supply chain in North America. Certainly we have some of the metals in Canada. The lithium is available, obviously, in South America. There are graphite mines in various places. So we need to compact everything, but also have much more efficient mining techniques. And some people would say we need to move away, certainly from cobalt and maybe from nickel as well. Manganese mining is less energy intensive. And what's the second part of your question?
It's about recycling. Do you think that the problem of the supply chain will be solved by recycling batteries, lithium batteries, I mean?
The answer is yes, but it'll take at least 15 years because a typical lifetime of a car is about 12 to 15 years. The oldest Teslas may be just about ready to be recycled, but there are not many of them. So it will take a long time. By that time, when they start recycling them, probably most of the lithium, nickel, and cobalt, most 30 to 50% will come from recycled product lines, not from original mining. And obviously, eventually, when all the vehicles are electrified, it should be similar to lead acid batteries, so most of the new batteries come from the old batteries. But it's going to take several decades for that to happen.
Okay, thank you very much.
Okay, thank you, Zedekino, for your question. Thank you, Professor Whittingham, for your answer. So the next question comes from the YouTube. The next question comes from Rebecca Cristina dos Reis. She's a chemistry student and she's in the room. Rebecca, would you like to make the question yourself or do you want me to read it for you?
I can try.
Okay.
Good morning, Professor. It's an honor to be here to hear you, and thank you a lot. Recently, we had the addition of sulfur to the ion lithium batteries. Could you talk about the limitation for ion battery and what challenge must be overcome, and which model did you expect to be ideal?
You're talking about adding sulfur?
Yeah.
Yeah. So if we had the ideal situation, we would have a lithium sulfur battery. Lithium sulfur battery would have about double the energy density of today's batteries. But sulfur is very difficult to handle. It's a super insulator, so it's very difficult to get the electrons in and out. It also tends to be soluble in the electrolyte solvent, so then diffuses over to the lithium and reacts with the lithium directly, not electrochemically. So we are looking at lithium sulfur in our battery 500 consortium. It's my belief is it will require probably a solid electrolyte, so we actually physically separate it from the lithium anode. But I think that holds the biggest promise, particularly if people really want to have electrified aircraft. There'll be small aircraft, but that's the only one that's going to achieve over 500 watt-hours per kilogram. So I think it needs more research. It's a tough research area, and so it will take a while to be commercialized. But that is a future area and one where we need lots of research done.
Thank you so much.
Okay, thank you, Rebecca, for your question. Thank you, Professor
Thank
Whitman,
you, Professor Luis,
for your answer. Next question comes from Professor Romeu Rocha Filho, who, as I said, is the president of the Brazilian Chemistry Society. Professor Romeu, would you like to make the question yourself?
Yes, I can. Well, thank you very much, Professor Whittingham, for this excellent seminar. Thank you for sharing with us your deep knowledge of lithium-ion batteries. My question is whether you could make a comment on how lithium-ion batteries fare against redox flow batteries for stationary applications.
Lithium-ion batteries dominate today, I think, of all the grid storage online right now. Lithium-ion has well over 95% of it. There's a little bit of lead acid. There was a vanadium flow redox battery in the state of Utah. If you look at them, they look more like a chemical plant. You're pumping things around. That means you've got to have somebody professional there to look after it, which means there's maintenance issues. And right now, I don't totally understand it. It looks like the utilities are going for the highest energy density batteries, not necessarily the lowest cost or what I would say are the safest ones. So it appears that energy density is more important to them than anything else. But I think in time, we will not have enough lithium to build thousands of 100 gigawatt hour storage facilities. We're going to have to go to flow systems, and flow systems have the advantage we can separate the amount of power coming out and the energy. It's much more like pumped hydro. So you can change the size of the reservoir depending on how much energy you want to store, independently of how much power you generate at any one time. So I think it's going to happen. The big challenge will be, can they get the cost down to where utilities will buy it, when you consider that lithium-ion is $100 a kilowatt hour today. It's anticipated it's going to go down to $50 or $60 per kilowatt hour. So there's a cost issue as well as others. But it could be in 5 or 10 years, the lithium price will increase much more as the demand keeps going up. So they may become competitive. But it's going to take time, and they may get into some niche markets first.
Thank you.
Thank you for the question.
So thank you, Professor Hamill, for your question, Professor Whittingham for your answer. So we have questions from YouTube. This one comes from Wagner Brocchini. He would like, he says that it seems that the power delivery is closely related to the surface area of the geometry selection. This meatball arrangement provides greater lithium contact as opposed to prismatic shapes.
Yep, so this is the challenge. The higher the power you want out, the more the surface area you want. The more surface area you have, the greater the side reactions. So the lifetime of the battery will decrease as you increase the power capability of the battery. So you basically design the battery to be either a power battery or energy storage battery. And in most applications, we actually make the electrodes thinner for the power batteries rather than making the particles smaller, because there's too many side reactions. So then the energy density goes down. So there's a lot of interest, obviously, in fast charging, but fast charging will damage the battery eventually. So you'll lose lifetime. So there's a trade-off when you make a battery between particle size, lifetime, power you want out of it. And there's a lot of interest today in making what we call single crystal batteries, similar to our original TIS2. They will have a lower power density, but people like Tesla and Jeff Dahn say they will last for 1 million driving miles. So you have your trade-offs. You have to pick what you want now. So you can have your small little sedan, which will get you around town low cost. Or if you want your supercharged, 150 mile an hour car, it'll cost you far more, and you'll probably wreck it before the battery dies.
Okay, thank you, Wagner, for your question. Professor Whittingham, for your answer. Next question comes from Satish Kumar VH from Unirio in Rio de Janeiro. Satish, do you want to make the question yourself, or do you want me to read it?
Thank you, Luis. Thank you, Dr. Whittingham, for the talk. My question is about the operational temperature of lithium-ion batteries. Has it improved over the range? Has it been widened over the years? Because recently we had this exploding laptops in the news, and of course last week the problem with the Texas thing. The governor took no time to blame this on renewable energy, of course. And we have extreme variations in International Space Station, right? So to be able to use lithium-ion batteries under these extreme conditions, how do we do this? Thank you.
So to address maybe the Texas situation first, it was not the wind turbines problems. And some of the photographs they showed of ice on the wind turbines was, in fact, fake news. Those wind turbines were from Sweden, not from Texas.
And they don't cause cancer.
Yes. So the issue in Texas is they don't get very cold very often. So the equipment is not winterized. And I work for Exxon. The Exxon refinery is not winterized. So if it gets very cold there, they often have to turn it off. The issue in Texas was, in fact, on the gas-powered power stations, nothing to do with the wind turbines. The wind turbines contribute between 10 and 20% of the energy. It was the gas-powered stations that went down because of the weather conditions. They need some water, and there's no water. So that was the issue there. The other part of your question, can you repeat it?
How can we make, has the operational temperature of the lithium-ion battery has been improved so that we can use in extreme weathers?
The answer is not really. We can use, the battery will work in the same weather conditions as you and I will work. So in extreme cold, you will not get so much power. So you need to warm it up. And typically, even the internal combustion engine, if you're in Minnesota here, not in Brazil, you will have a heater on in the night to keep the engine warm. So I think, and you definitely don't want to get it hot, so there's very good cooling systems in those batteries.
Was that the reason for the exploding laptops?
Those Samsung ones was bad design, and this is maybe where my comment about culture. I don't want to rap the Asians all the time, but remember, as a scientist or engineer, if your boss tells you to do something and you don't think it's practical or safe, tell him so. What happened in Samsung, as far as we can understand, is Apple had just announced their new phones and laptops, and the Samsung chief came in and told his engineers, you've got to put 20% more battery into these phones, and there really isn't space to put 20% more in. The engineers didn't respond, no, we can't do that. They did it. A lithium battery in its first few cycles expands a bit. So what happened is on charging, they expanded, crushed the separator, and dead short. So it was basically a very bad design issue. And it was the same issue with the 787 lithium-ion batteries. It was a design problem, and it should have been picked up. And I think probably the Asians have understand now. Listen to your engineers. Let them determine the safety. They're never going to cram more stuff into a given space than that's reasonable. So, but you haven't heard about any other laptops really catching fire since 10, 15 years ago when several IBM ones did. So people know how to design the batteries for laptops to make them safe. And even when they fail today, they fail in a safe manner. So you'll find your laptop just stops working, and you can tell the battery's probably swollen a bit, but it will not catch fire. It will just by itself turn itself off before anything goes wrong.
Good to know. Thank you.
Okay, thank you very much. Let's move to the next question. So it comes from Gustavo Dobeck from Unicamp in São Paulo, Campinas, São Paulo. Gustavo, do you want to make the question yourself?
Yes, I can also do it here with the camera. Thank you very much, Professor Whittingham, for the nice talk. My question is not so much a question, but more like a comment that I will be interested on you with your experience regarding conversion cathodes, or more unusual ones, like the one that you already mentioned, the lithium sulfur system, or even the lithium oxygen system. And what should we be looking at for those systems?
So in our large consortium, the EFRC, we looked for 5 years at conversion cathodes. And Glenn Amatucci led our effort there. We looked at iron fluoride, iron oxyfluoride, FEF3 as well as FEF2, FEOF. The issue in those, we found the discharge reaction and the charge reaction were different. So we had a large voltage difference between charge and discharge, which made them very energy inefficient. So you lost a lot of energy, which obviously utilities wouldn't be happy with. Also, you tend to get, on these conversion reactions, the powder tends to get finer and finer on each part, in each cycle. So they become more reactive with the electrolyte. There are people still looking at them. If we can solve the reaction mechanism, then they might be viable. They clearly have a much higher capacity, but the voltage tends to be somewhat lower. Lithium sulfur is the best bet. I think lithium oxygen, people have, I won't say totally given up on, but it doesn't seem to have many advantages. You've got to, as far as we can tell, you have to use pure oxygen. CO2 and water will kill the system. And volumetrically, its energy density is poorer than today's lithium-ion. So it's only good on a weight basis. There are some lithium oxygen cells, primary cells, they work well. And Polyplus in California is using those in some ocean buoys. And they basically use the seawater as the cathode material. But I think a lot of people don't believe lithium oxygen is viable as a high energy density system. So lithium sulfur, yes. If some of the fluorides, maybe if we can solve the reaction mechanism, but whenever you've got fluorides, you've now got this problem of these hazardous gases and liquids that might be formed during reaction and during recycling, called PFAS. And a lot of people are worried about getting those into the environment.
Thank you. Thank you very much for your answer.
Okay. Thank you. Professor Whitman, we have still some questions. Can we move on with these questions?
Yeah, that's fine.
Oh, okay. So let me first ask if José de Aquino, he wrote down a second question. Would you like to make the second question, José de Aquino, or should we move on?
Yes, I can. I'd like to know about aqueous lithium-ion battery. Do you think that to circumvent the problem of inflammable organic electrolytes, is it possible to use aqueous electrolytes, for example, using water and salt electrolytes? Is it possible?
I think folks have shown it's possible. I'm sure it's not economically viable because you've got a huge amount of salt in there and the salt is expensive. So in the end, you have to look at what the composition of the entire battery is. So in our batteries where we're getting 350 watt hours per kilogram, there's absolute minimal amount of electrolyte in there. If you open them up, nothing would probably drip out. So it just soaks into the porous media. So I think they're interesting scientifically. That may give us a better understanding of how batteries work. But you have to do a cost analysis to see how much all the components cost per kilowatt hour.
Okay, thank you very much.
Okay, thank you. So another question from YouTube again, Wagner Brocchini. He says, one last question is about chemistry safety. Have tests been conducted for features like puncturing, over-discharge, and overcharge tolerance of these cells?
Yeah, this is done all the time and has to be done because they have to get underwriters lab certification. And quite often these involve nail penetration tests. In the old days, they used to shoot a bullet through them, but that's not the same as a dead short. So you have to have shorting tests, internal as well as external. So these tests are done routinely. In the lithium-ion battery, every single cell is electronically protected. So you should not be able to either overcharge or over-discharge. So in the Tesla car, there's electronics in there to prevent that. If a cell goes bad, it gets taken out of the circuit and that part of the battery isolated. So there's a huge amount of electronic protection. No, you don't have that in lead acid batteries because if you overcharge or over discharge, you just generate hydrogen and oxygen. In the lithium-ion battery, there's no such safety valve built in. So you have automatic cutoff at certain voltages. So if you ever buy a cheap replacement batteries for your phone, don't. It might not have the proper electronic protection in there.
Okay, thank you very much. So we are getting to 1 hour and a half, so maybe let's allow a last question by Carla Real from São Paulo, Campinas. Would you like to make the question yourself, Carla?
Yeah, I can do this. So we have a group here, the Center of Innovation New Energies, and we study supercapacitors, and we are starting to study batteries. So I want to know that do you think about alternative batteries to lithium-ion, like sodium or potassium-ion batteries? They can replace lithium batteries in the future?
So people are looking at a lot of different batteries, both intercalation-based, which would be sodium and potassium. I think we need to study sodium and potassium so we better understand lithium-ion batteries. I don't think potassium-ion batteries will ever be viable. They may have a good energy density, but potassium melts at about 60 degrees centigrade. So if it melts and you've got an organic solvent there, you've got a bomb on your hand. So I think they're extremely unsafe. There's a lot of interest in sodium batteries because clearly there's no limitation on the amount of sodium in the world. And sodium works with lower cost cathodes. You can make a layered oxide out of iron and manganese. So that would work. But right now they are lower energy densities. And as far as we can tell, all the customers want high energy density. But if we go to very large grid storage, I think sodium may be the wave of the future. But it'll depend on the particular application. But we need to understand sodium better. We need to start making sodium batteries and testing them in various applications. So yes, on sodium.
Oh, okay. Thank you, Carla, for your question, Professor Whittingham, for your answer. So, well, I mean, as I said, we are with 1 hour and a half, but we still have 100 people around attending to this webinar. But I would like to ask everybody to turn on their microphones once again for a final round of applause in retribution for this excellent webinar that we had today. Thank you very much, Professor.
Thank you, Professor.
Thank you, Professor.